In this video, we're going to be evaluating definite integrals using U substitution. And when we do that, it's called a change in variables. A lot of books will give you some notation like this when they describe it. I think it makes it kind of complicated to say that U is going to represent a function g of x, and so now I need everything in terms of g and u, and it's just kind of crazy. This may not be mathematically correct to call u a function, but we're going to do it anyways just because it simplifies and makes everything, I think, make a little bit more sense. So rather than saying that u is g, I'm going to just say u is u. So whenever I find an antiderivative using u substitution, that is because our function is a chain function or a quotient or a product. And so when I do that, I am integrating in terms of u. But when I do that, I need to change my upper and lower limits in terms of u as well. So when I come up with my u equation, I'm actually going to evaluate my upper and lower limits in that equation and change those upper and lower limits. And I'll show you how to do that. So anytime we have a function that's a chain or a product, we're going to find the antiderivative using u substitution. And in general, with a chain function, the innermost function is going to be our u equation. So if I say u is x squared plus 1, then I can substitute that and say u cubed instead. And then I'm going to do a couple more changes. I'm going to shift that x to the back. So now I have u cubed x dx. And we're also going to change our upper and lower limits here in terms of u. So now that I know what u is, I can plug in my upper and lower limits and get my limits in terms of u. So if I plug in my upper limit into my u equation and simplify, 1 squared plus 1 is 2, so I can change my upper limit to 2. I can do the same thing with the lower limit. So if I plug 0 into my u equation here and simplify, I get 1. So now I can change my lower limit of integration to 1. So now my limits of integration are in terms of u. I just need to do one more thing, replace my x dx with something that's in terms of du. So I'm going to take my u equals equation, I'm going to derive both sides, and I get du equals 2x dx. And I know that I want to substitute x dx. So to get x dx by itself, I divide both sides by 2. So now I can substitute 1/2 of du for x dx. So replacing x dx with du divided by 2, changing x squared plus 1 cubed into u cubed, and changing my upper and lower limits in terms of my u equation. One more step before I actually integrate. I'm going to take that 1/2 constant out to the front, and now I can find my definite integral. We're going to use the power rule. We're going to find our antiderivative. We get u to the 4th over 8. So I have u to the 4th divided by 4, and 1/2 times that gives me u to the 4th over 8. So I'm going to take that antiderivative and I'm going to evaluate it using the fundamental theorem of calculus. That's the f of b minus f of a. So we're going to use our upper limit and our lower limit and plug them into this function and subtract. So evaluating my antiderivative using my upper limit, my new upper limit of 2, I got 2 to the 4th over 8. And then I'm going to subtract my antiderivative evaluated at the lower limit, my new lower limit of 1. So if I plug 1 in, I get 1 to the 4th over 8. So subtracting these two values, I have 16/8 minus 1/8. That gives me 15/8. It is possible to do all of this without that change in variables. So what I could do is I could do all of these steps, find my antiderivative, and then I could back substitute what I replaced u for, and then evaluate it using the fundamental theorem. So I could be substituting my old upper and lower limits into this equation, and when I plug 1 in here and then subtract it from plugging 0 into here, we actually end up with the same difference, 16/8 minus 1/8, and we get the same answer, 15/8. It's a little bit easier to evaluate by using that change of variables, but it's not necessary. If you want to back substitute what you originally replaced u for and then evaluate using the fundamental theorem, that's okay as well. Let's do one more example. Once again, we got a chain rule. I'm going to use my innermost function to represent u. So instead of 2x plus 1 to the 1/2 power, I now have u to the 1/2 power. I'm then going to reevaluate my upper and lower limits using my u equation. So if I plug in my upper limit of 4, I get 9. So that's my new upper limit. If I plug in 0, I get 1. That's my new lower limit, all in terms of u now. The last step I need to do is replace that dx with du. So let's derive both sides of my u equation. We get du equals 2dx. Just to get dx by itself, we divide by 2. So we can substitute 1/2 du instead of dx here. Shift that 1/2 constant out to the front. And now we can evaluate this definite integral. Again, we're going to use the power rule. We're going to add 2 halves. We're going to add 1, which is 2 halves, to the exponent and divide by that. So we get 3 halves is our new exponent. We divided by 3 halves, which is the same as multiplying by 2/3. So I'm going to multiply that 1/2 that was out front by that 2/3 now and get 1/3. So I got u to the 3 halves over 3. That's my antiderivative. We can evaluate that using our new upper and lower limits. So if I plug in 9 first, 9 to the 3 halves divided by 3 minus plugging the 1 into the antiderivative. So we get 1 to the 3 halves over 3. Let's simplify that. The square root of 9 is 3, and 3 cubed is 27. The square root of 1 is 1 to the 3rd power is 1. So 27/3 minus 1/3 is 26/3. And again, we could do that slightly differently without using that change in variable. If I want to back substitute my u into my antiderivative and then use my original upper and lower limits to evaluate using the fundamental theorem, we could do that, and we should end up with the exact same answer.